To Mana Studies. Let's begin with today's topic, that is relation, which is part 2 of sets. Now, what does relation mean? In Hindi, it means संबंध. अगर दो elements एक दूसरे से किसी भी तरह related हैं, then they fall under this topic. Let's take the example of a coordinate plane. अगर हमारे पास कोई point है, let's say that the point is A. Now, how will I pinpoint to the location of the point? Let's say the distance from the origin on the x-axis is denoted by A and the distance from origin on the y-axis is denoted by B. Then the points of the the coordinates of point A will be denoted by A comma B, and the technical terms are abscissa and ordinate. Now the two terms A and B are related according to the coordinate plane in order to pinpoint the location of a point. So they are known as an ordered pair because AB is not the same as BA. BA would pinpoint to some other point. Let's take an example. On x-axis, if I have the point as 1, and on y-axis, if I have the point as 2, then the coordinates will become 1, 2. And if I revert them, then on x-axis it will become 2, and on the y-axis it will become 1. So the location would be 2, 1. As we all know that these 2 points are not the same, therefore we can say that in the ordered pair, the sequence in which the numbers are written is of paramount importance. Now let's take a step forward to Cartesian product. Now what is Cartesian product? If I have a set A and another set B, then the elements one from set A and one from set B, they will be written together in the form of an ordered pair. This set of all such ordered pairs is known as the Cartesian product of the two sets. Now if we talk about the number of elements in the Cartesian product, let's take an example. Let's say the set A comprises of 1, 2 and set B comprises of two elements A, B. Then the Cartesian product of A and B will be written as 1 with A, 1 with B, 2 with A, 2 with B. These will be the four elements of the Cartesian product A cross B. So it will be appropriate to say that the number of elements in the Cartesian product will be the same as product of the elements individually in each of the two sets. Now the third point is that the two ordered pairs, that the ordered pairs of A cross B and B cross A will not be the same. As we had seen in the previous example, if I take the same case again and write them as 1, 2 and A, B, then in A, B, the elements would look something like 1A, 1B, and so on. Whereas in the case of B Cartesian A, they will become A, 1, A, 2, B, 1, and so on. As we focused at in that coordinate figure diagram, that the point 1, 2 is not the same as the point 2, 1. Similarly, this 1, A is not the same as A, A. So it will be appropriate to say that these two are not equal. Now let's move forward to the next point, that is if at least one of the sets is a void set. If I say one is a void set and if I have to create the Cartesian product with some other set which has three elements, then the Cartesian product of these two sets will be a null set. Now we have certain important points. Relation R is defined from a non-empty set A to a non-empty set B is subset of A cross B. Now let's say that we have two sets, one is A and the other is B. A relation is going to be defined from set A to set B. Let's say the set A has three elements 1, 2, 3 and B has three elements A, B, C. If they are related in such a manner, then it will be appropriate to say that relation is a subset of the Cartesian product, because in this case the relation can be written as 1, A, 1, 2, B, 3, C. Now this is a subset of all the elements of the Cartesian product. The Cartesian product would also include 1, B, 1, C, but they are not present in this relation. Now domain of R is the set of all first elements of ordered pair. As in the previous case we had seen, in the two sets A and B, the elements of the set A, they are known as the domain. Domain are all the values that we can input, Then we have the next term, which is range. Range includes all the values in the second set, that is set B, that are somehow linked. If I say that the relation is defined like this, then the range will be D, E, and F. And then comes the term codomain. The entire set B is known as the codomain. Now it's a point of confusion for many. Codomain is not always equal to range. This is not true. Generally, they are unequal. There can be a unique case in which the range and codomain are equal. Let's say if it did not comprise of G, then range and codomain would have been equal. But in general cases, range and codomain are different from each other. Sorry, I missed the point. Universal set. Now, not universal set, universal relation. If any set A, if any set A is said to be defined, if a relation is defined on A, if a relation is defined on A, then that means that relation can be written as A cross A. Now we are going to take the Cartesian product of A along with A. So it will comprise of how many elements? 3 elements over here and 3 elements over here. So the number of elements in this will become 9. And the Cartesian product would look like 1 1, 1 2, 1 3, 2 1, 2 2, 2 3, 3 1, 3 2, 3 3. All these are ordered pairs which will be present in the relation which is known as universal relation. Now void relation would be an empty relation, it will have no elements. Then comes identity relation. Now what's an identity relation? Identity relation is when the element in the first set is the same as element in the second set. Now let's solve this question. Let A is equal to let A is a set comprising of 1, 2 and 3. There are 3 elements and R is defined on A. R is defined on A means that the relation is defined on A Cartesian A. Then R can be written as A comma B, where A plus B is equal to 3. So let's write down the entire product. Cartesian product, it will be 1 1, 1 2, 1 3, 2 1, 2 2, 2 3. Similarly 3 1, 3 2, 3 3. All these are ordered pairs which will be present in that relation. Now the question says the relation is defined. Now this is the condition as we talked about in the first slide, sambandh. The relation is explained by this condition where A plus B equals to 3. Is 1 plus 1 equal to 3? No. Is 1 plus 2 equal to 3? Yes. Not over here. Yes over here. No. 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 And obviously no. So the relation will comprise of, I've written A cross A over here, and the relation will be 1 comma 2, that is an ordered pair, and the other ordered pair is 2 comma 1. Now because the order in which they are written matters, hence 1 comma 2 is not the same as 2 comma 1. Let R, which is the relation, is defined on A as A comma B belongs to, and this is the condition which has to be followed. 2A plus B equals to 5. Again, when R is defined on A, that means relation is defined on A Cartesian A. It can be written as 1 1, 1 2, 1 7, then 2 1, 2 2, 2 7. Similarly, 7 1, 7 2, and 7 7. Now we have 9 ordered pairs. There has to be a comma in between because they are different and not any 2-digit number. So now let's satisfy the condition which says 2A plus B equals 5. If B is equal to 1, then 2A should be 4. That means A should be 2. So this is a member. If B is equal to 2, then 2A is equal to 3. A is equal to 3 by 2, which is not possible. If B is 7, it becomes negative. So there is only going to be one element which will satisfy that condition, and that is 2 comma 1. Now this is the solution to that question. Let's move forward to types of relations. Now types of relations are divided as, first is reflexive. Now reflexive is similar to identity relation but not exactly same. In identity relation we saw that A comma A should be present. If the three elements are 1 2 3, Then identity relation asked for 1 1 2 2 and 3 3. This was the identity relation. Whereas in the case of reflexive relation, now it's a bit different. All these must be present, but if any extra ordered pair is also present, still it will be reflexive. Now let's solve this question. Let L is a set of all lines in a plane and relation R is defined on L as L1 relation L2, which says L1 is parallel to L2. If we follow that reflexive condition, is L1 parallel to L1? Obviously. Is L2 parallel to L2? Yes. Is L3 parallel to L3? Similarly, Ln is also parallel to Ln. So we can say that this relation R is reflexive because it will constitute of all the lines as they are parallel to themselves, and even if any line is parallel to some other line, let's say L1 is parallel to L5, even that will be included, and that is also all right for the reflexive case. It won't be an identity relation, but it will be reflexive. Now the second one is symmetric relation. The condition is any relation R is called symmetric if the ordered pair A comma B and the ordered pair B comma A both belong to that relation. The question is, let L is a set of all lines in a plane and relation R is defined on L as L1 relation L2, where L1 is perpendicular to L2. Now we know that if L1 is perpendicular to L2, then automatically L2 is also perpendicular to L1. Hence we can say that this is a symmetric relation. Now let's solve the last one, that is a transitive relation. Transitive relation simply means that if A is related to B and B is related to C, then if we can say that A and C are also related, only then can we say that the function is transitive.